Hello, thank you all for joining us today in our webinar. Today we are going to be talking about how to improve safety and reduce false trips, how to configure the safety transmitter interface. For those of you who do not know me, my name is Loren Stewart. I am a CFSE and I work here at exida. I work mostly with our mechanical customers doing on-site audits and FMEDAs and safety cases, but I also work with our end user group in training as well as research. In case you do not know who exida is, we're going to tell you a little bit about us first. I like to say no matter where you are or where your customers are, we have a facility or someone close by to help you in any of your functional safety needs, whether that be functional safety, alarm management, or cybersecurity. You can break exida up into 4 major industry focuses, starting from the beginner in the OEM and engineering contracting side to system designer and end user. We have consulting services and help with functional safety needs, but also tools and software to help you do functional safety and training as well. Our engineering consulting services, like I mentioned just a little bit ago, we have our functional safety or our process safety sector, our alarm management, and our cybersecurity. We have engineering tools and software to help you save time and save money while increasing your efficiency and productivity. So whether you're trying to perform PHAs, LOPAs, SIL verification, you're making your proof test procedures, or assessing your risks or alarm rationalization, we have an engineering tool that can help you save time and money. We also have certification, and we have certification that you might be familiar with for our functional safety, IEC 61508 and 511. We also have our tool qualification, ISO 26262, and our cybersecurity, our machine safety, and our personnel safety. So we can certify you that you are a personnel expert in functional safety. But today we're going to talk about safety certification and the certified transmitters when they can, with their diagnostics and sending the output levels to out of range. We're going to talk about if the safety PLC is correctly configured to interrupt these currents, safety can be improved, and false trips can be reduced. So today we're going to look at the configure of the safety transmitter interface. The sensors in a safety instrumented system are used to measure the process variable conditions that indicate a potential hazard. Therefore, several design issues are very important. The design must select equipment that is suitable and has sufficient safety integrity, equipment that has realistic failure rate data. The design must be properly utilize the automatic diagnostics, consider and plan for manual proof testing, and also include any necessary redundancy needed for safety and availability. The first and most important consideration when selecting sensors for safety applications is that they accurately and reliably measure the process variable. Another key issue is that any process-wetted materials must be compatible with the chemicals of the process. Usually these are the same, the process variables that are used for control. Successful operation in a similar process control application is a good indicator of process compatibility for the safety application. Like all equipment used in your safety system, a sensor device must also be justified based on your safety integrity. So fortunately for the industry now, it's evolved to a point where there's been many different sensors certified for IEC 61508. The number of manufacturers and technologies are quite large, such that few engineers now need to spend the time creating their own prior use and safety integrity justification. The IEC 61508 certification process is quite rigorous. And so when you have an accredited third body go in and evaluate per the IEC 61508 requirements, that really speaks about the product that is being certified. These safety critical and safety certified devices are a special class of products and have advanced automatic diagnostics that can detect many of the internal failures. If you want a list of valid, current, and valid IEC 61508 certified devices, they're maintained at a website called the SAEL, the Safety Automation Element List. And you can find that at www.sael-online.com. The most common measurement in your safety instrumented system application is pressure. So let's start with our equipment selection, looking at some pressure devices. And fortunately for instrumentation products available in this application are well proven and highly advanced. If you look on the SAEL, there are several products that are already certified per IEC 61508. And this is just an example of one of the most common transmitters, the Rosemount 3051S. It actually received its certification for IEC 61508 here at Exida over a decade ago. And as one of the most popular transmitters in the process control market, the 3051S has accumulated substantial proven in use hours during the many years it's been out in the market. The product safety manual provides failure rates. It will provide failure modes, suggested proof tests, proof test coverage estimates, and all of the settings that need to be considered when you're evaluating a product for your own safety application. Temperature is another common measurement in a safety instrumented system application. The instrumentation products available for temperature measurement are also quite mature and highly advanced, with several well-proven products available and some that are IEC 61508 assessed also. Here is an example. We're looking at a More Industries International STZ, and it's received its product certification for IEC 61508 in 2015. It is capable of using 2 temperature sensing elements and can be set up to provide comparison diagnostics with the transmitter. This feature provides a high diagnostic coverage on the sensing elements. This example, this STZ, is rated for SIL 2 in a single application or hardware fault tolerance of 0, so no redundancy, 1 out of 1 configuration, and a SIL 3 with a hardware fault tolerance of 0 architecture, of greater than 0 architecture. Whether that would be a redundant system, 1 out of 2, 2 out of 3, 1 out of 3 system, anything higher with higher redundancy. And you can go on the SAEL to see more temperature sensing equipment and see many that are SIL 2 and SIL 3 rated. Level is another common piece of equipment in SIS applications. It is used in separation units to prevent high pressure or blow-by and is common in tank farms. There are a number of different technologies used to measure level. Sensors are available as either level transmitters that send a proportional analog signal or level switches that send a Boolean value. Both types of products are available, and with 2-wire 4 to 20 milliamp interfaces. Level switches are also available with contact switch output. For one example of a level switch, we are looking at this is the Magnetrol E3 module level displaced transmitter. And this is another level transmitter certified for SIL 3 capability. This device uses a different method of level measurement. It actually is a buoyancy force acting upon a spring supported displacer caused by a liquid level change. If you want more examples of level switches and level transmitters, you can look on the SAEL for more certified devices. Then we come to flow. Flow measurement is important to many safety systems. There are many different technologies available with different capabilities and features available to measure flow. The SIF designer must choose the instrument best capable of accurately measuring the specific application flow. So fortunately, there are many products that have the IEC 61508 certification already done for you. Right in front of us, this is one example. This is the Micromotion 1700-2700 Coriolis flow meter, and it received its product certification per IEC 61508 in 2005. And the basic technology is frequency-based, providing high inherent safety, as most internal failures will result in lack of frequency and therefore are detected by the transmitter. What about diagnostics? The advantages of the advanced automatic diagnostics in a sensor device depend upon a failure detection signal reaching the logic solver. The logic solver must be configured to either vote the sensor, so it will vote the sensor, it'll signal to either trip or to enunciate the failure to the plant repair team or the operator, so that a repair team can make a repair and the failure can be restored back to the correct operating conditions. Without enunciation and an effective repair, the diagnostics are not effective and cannot be given credit in a safety system or for safety function analysis and calculations. Many sensors that use a 4 to 20 milliamp analog current to signal the process variable also use the current level to signal an internal failure detected by automatic diagnostics in the sensor. One common set of current values used for this purpose are based on the NEMOR NE43 recommendations shown here. It is essential that the logic solver be connected to these sensors that are programmed to detect a current less than 3.6 milliamps or greater than 21. A choice is then made to interpret the signal as a trip indication or not. In non-redundant architectures such as 1 out of 1 and also redundant 1 out of 2 sensor architectures, most engineers choose not to trip, but instead just to enunciate a failure alarm to the maintenance team. And this is done to avoid those false trips when a sensor fails and the probability of failure upon demand is not impacted significantly. It will be impacted, but not significantly, if the restore times are less than 1 week. For a 2 out of 3 redundant sensor architecture, the logic solver may or may not be configured to vote to trip, as the redundancy would avoid a false trip. However, in both cases, a failure alarm is sent to the maintenance team. Depending on the logic solver, 1 or 2 scan delays may be needed as well to avoid false trips as the analog signal transitions from its normal to current level to a failure indication current level. Many logic solvers have pre-configured input blocks with all appropriate logic already designed and already tested. On your screen, you're looking at input channel parameters that can be set in the Emerson Delta V SIS with electronic marshalling safety PLC to enable the NEMOR failure detection. The overrange and underrange can also be used if the values other than NEMOR are needed. Another approach is used in the Moore Industries STA. The input limits are entered as parameters. When the input current goes outside of the limits, a fault relay output from the module is activated. When diagnostic annunciation is performed correctly, the probabilistic modeling can give credit for the automatic detection. Safety is improved and false trip rates can then be avoided. Failure rate data for sensors is often presented using functional failure modes, not the IEC 61508 failure modes that you might be familiar with, such as the safe and dangerous, broken up into detected and undetected, because most sensor devices can be used in different applications, such as high trip or low trip or high-low trip. It is often not possible to know which failures are safe versus dangerous at just the sensor device level without knowing the application and the logic solver configurations. So here's an example of probabilistic modeling of sensors. We are given failure rates for this pressure transmitter according to different failure modes. You have your fail output high, which would be greater than 21, fail output low, which is less than 3.6. You have your fail if output is frozen undetected, fail output drift high undetected, fail output drift low undetected, failure detected, and failure of diagnostics. Each of those has a failure rate associated with it, along with failure modes. The parameters of the failure modes of a pressure transmitter might cause a false trip or a safe failure, may cause a dangerous failure, or generate a diagnostic alarm in the safety PLC if the failures are detected by an internal automatic diagnostics. The application must be considered when classifying these failures into categories such as safe detected, safe undetected, dangerous detected, dangerous undetected, no effect, and so forth. So, with those failure rates from the slide previously, we're going to think of an example. A pressure transmitter has internal automatic diagnostics that detect most internal failures. This transmitter has failure modes and failure rates per what the table we just reviewed. It is being used as a single sensor, so a 1 out of 1 application, no redundancy, in a SIF to de-energize its output to initiate a process trip when pressures exceed 80% of scale, 16 milliamps. This transmitter is connected to a safety PLC that is programmed to detect under range at 3.6 or lower, or over range at 21 or greater current signals, and sends a diagnostic alarm to the repair crew. The safety PLC has a trip delay on analog input to prevent any spurious trip when the current makes its transition from active value to failure condition. The pressure transmitter is programmed to send its output low on detection of a failure to avoid false or spurious process trips. Using the failure mode definitions, how would these failures be classified? So the first instance is when the transmitter fails with its output saturated over the 21 milliamp range, the transmitter output will go up through the trip point. The safety PLC will interpret this as a failure of the transmitter and send a diagnostic alarm. No false trip of the SIF will occur because the PLC is programmed to recognize this. not as a trip, but as a failure in the transmitter, and the PLC has a trip delay in the analog input to prevent any transitional input scans from causing a spurious trip. So these failures do not meet the definition of fail-safe. However, the transmitter is not capable of responding to the demand until the repair is made. So the failure class would have to be dangerous detected. The next, when a transmitter fails with its output saturated under range, so less than the 3.6, the transmitter output will go away from the trip point. The safety PLC will interpret this as a transmitter failure and send a diagnostic alarm. No false trip of the SIF will occur as the transmitter output does not go through the trip point. So just as the last one, the transmitter is not capable of responding to a demand until the repair is made. So the failure is then detected or classified as dangerous detected. When a transmitter fails with its output frozen, it is not capable of responding to a demand. If this is the situation, if this situation is not detected by any internal automatic transmitting diagnostics, and the current will be in the active range, it then has to be classified as dangerous undetected. What about when a transmitter fails with its output drift high and it's not accurately signaling the process measurement, yet the current is likely in the 4 to 20 milliamp range? The current is drifting towards the trip point, so this failure may cause a false trip. If this situation is not detected by any internal automatic transmitter diagnostics, it will have to be classified as safe undetected. When a transmitter fails with its output drift low, it is not accurately signaling the process measurement and it is drifting away from the trip point. The current is likely in that 4 to 20 milliamp range. If the situation is not detected by internal automatic transmitter diagnostics, it will have to be classified as dangerous undetected. What about when internal failures that are detected by automatic diagnostics within the transmitter will send the current to the predefined value specified in the transmitter? In this case, if the current level goes below the 3.6 milli range, and as long as the current level goes out of range, the actual level does not matter, as the safety PLC will detect either the high or the low and send a failure annunciation to an operator or repair team. However, the transmitter is not capable of responding to a demand during this time, so the failure would be classified as DD, or dangerous detected. And finally, the final example is failures within the transmitter that cause loss of diagnostics do not affect the safety function, so these failures could not be classified as either safe or dangerous. The effect of these failures on safety integrity is likely small, but these failures could be modeled for more accuracy. These failures will just be defined as annunciation undetected. So when we go through each line of the previous example, we can then classify similar categories with each other. So we go and look at all of the failure rates that we classified as dangerous, detected, and we can add those together. So you're going to have your failure rate of your fail output high. That would be dangerous, detected. Fail output low is dangerous, detected, and fail detected is dangerous, detected. Adding up the failure rates that we were provided with before, we then come with your total dangerous detected failure rate. The failure rate categories for this example are, and all of the examples normally found in functional safety are in FITs. That is failures in time, and FITs are failures per billion hours. So the next example, let's think about a transmitter, a 1 out of 1 architecture fails, and its output saturated over range, so it's greater than 21 milliamps in a high trip application. A false trip of the SIF will occur as the transmitter output goes through the trip point, and the PLC is not programmed to interpret this as a transmitter failure. So in this situation, the failure mode is classified as a safe, undetected failure. So some people listening might think, well, why undetected? If the transmitter causes a process trip, well, then it's detected. Well, yes, that is true, but the definition of undetected refers only to automatic diagnostics within the SIF, already not recognized by our operations personnel. So this is done to allow the failure rates to be properly used in a model of redundant architecture, including those where a safe failure of one transmitter does not cause a plant trip. The objectives of any effective proof tests is to detect any dangerous failures not detected by automatic diagnostics, to reduce maintenance effort, and to simplify procedures to avoid errors. The goal is to divide a simple test that can be done quickly and efficiently to find all the dangerous undetected failures you can. And this test strategy will vary depending on the sensor type. However, a common strategy is to include the sensing element in the test, include all sensing or sensor devices, including, for example, an impulse line or remote seal, intrinsic safety barriers, etc., to exercise the sensor output over its full range and over range, to inspect for physical damage, and to check for unauthorized sensor configuration changes. Manufacturers of safety certified devices who know the details of their product, they have already been planning proof test strategies as part of their product design process. One technique is to reduce the total proof tests in an effort to devise two proof test methods. One which is easy and quick but has a lower proof test coverage, and a second proof test which is more expansive. It is an extended proof test that has a higher proof test coverage. The intent of this strategy is to run a sort of combination of the two, the simple and the more complex, to be able to push out your more complex proof test as far as possible. Here on example, we have a page from the Rosemount 3144P temperature transmitter. This is a part of their reference manual. You have an abbreviated proof test that can be performed in the control cabinet room using a handheld device in a relatively short period of time. This test exercises the device output over the full range plus over range and exercises the most of the microcomputer systems. However, the sensing element is not tested in the abbreviated proof test. On the other hand, you have the extended proof test, which requires a minimum of 2-point calibration, which would take significantly more time in the field with the transmitter. This test adds a check of the sensing element and the temperature compensation circuit. So that's something that you wouldn't want to do very often. So maybe do your abbreviated proof test more often to push out the more expansive proof test longer. What about staggered proof test strategies? Well, in redundant sensor architectures, the proof testing actually can be staggered. For example, what if you have two transmitters that are used in a SIF? The SIF will trip either transmitter, indicates a potential dangerous condition. As an example, the proof test for transmitter 1 is performed every 6 months, and then the test is performed every year thereafter. Proof test number 2 for transmitter number 2 is done at the first year mark and then every year thereafter. So you have a 6-month stagger between proof test 1 and proof test 2. Although this method has been proposed as a way to reduce total proof testing and or to improve safety, realistic modeling has shown no advantage in terms of proof test effort or increased safety. Given the added complexity of this proof test scheduling, this method is not necessarily recommended. Multiple sensors are often used to sense a potentially dangerous condition, especially for a SIL 2 or higher application. These redundant designs may be intended to improve safety using a 1 out of 2 voting for 2 sensors in the logic solver. Or the design intent may be to reduce false trips using a 2 out of 2 voting for 2 sensors in the logic solver. 3 sensors using a 2 out of 3 voting in the logic solver can provide protection against false trip and improve the safety. So if you are able to, normally a 2 out of 3 design would improve safety and reduce false trips the best. Whenever multiple sensors are used for the same process measurement, the designer must consider common cause as a failure also. A common cause failure is defined as a failure of one or more device due to common stress event. So any type of stress, whether it is electrical surge or lightning strike or possibly humidity or bad environmental specs. The defense strategies to try and reduce common cause are one or more than one of these three rules. So you can reduce the common stress, whether it's separating them physically or separating them electrically or both. There is less likelihood of the sensors being subjected to a common environmental stress. Both physical and electrical separation are important. When a practical, redundant sensor should not be physically mounted side to side, where the physical and electrical common stress would be nearly identical if they're mounted side by side. Most environmental stress factors vary nonlinear, so even if you're just able to move them a small distance or a small physical separation, it will have a major impact on your common cause. You could also apply diversity. Diversity is a concept in which differently designed sensors are used in a redundant configuration. The motivation is that the different designs will not suffer from the same common cause design faults. In addition, sensor manufacturers, they manufacture different designs and using different components will not suffer from the same manufacturing faults. In terms of environmental stress, the diverse redundant sensors are effective only if the sensors respond differently to that common stress. The use of two different manufacturers' devices may provide some benefit considering the lower possibility of common design and manufacturing defects. But significant benefits will not be realized if the sensors have used the same technology and respond similarly to the same common stress. A mechanical unit backing up an electrical unit would be a good application of hardware diversity. Even in a well-designed, diverse, and redundant sensor subsystem must consider several trade-offs. System-level design errors are more likely to occur due to many problems with sample synchronization, calibration, and data mismatch due to digital round-off. So there can be extra effort required for extra design training, extra design documentation, extra maintenance training. You're going to have extra spare parts, extra checking in effort to avoid all of these faults and make sure you're on the right device at the right time. So the use of different sensors adds maintenance and operation complexity as calibration procedures and repair procedures are going to be different. So all of these negatives may override the benefits of diversity. Consider a design where 3 smart safety certified pressure transmitters from 3 different manufacturers are chosen to be a 2 out of 3 architecture. All 3 transmitters use a diaphragm assembly. The calibration and maintenance procedures are different for each transmitter. The configuration tables are different. This design choice would not bring much diversity to defend against common cause, and would all likely cause setup and maintenance and calibration errors during operation. So the maintenance and operation problems may override the benefits for this type of diversity, especially if your maintenance and operations are good or average and you're not a near perfect facility. And then the final rule of trying to improve common cause is design for high strength. So sensors with rugged high strength designs are more likely to resist a stress event that might fail multiple units. So that is one of the reasons IEC 61508 requires more stringent design and testing procedures for higher SIL levels. Sensors with systematic capability of SIL 3 or SC3 are more suited in redundant designs, even with identical redundancy. So now I'm going to take a minute for questions. While I open that, I will have a slide up about our upcoming trainings. If we have trainings in the United States and in other countries for different applications all this summer. You see the questions. We don't have any questions at this point. If you think of any later, please email me. And if you think of any great webinar topics, please email Exida Academy. Thank you so much for joining us today, and hopefully you have a great rest of your day.